Hi, this is Chintan Patel. In this lecture, we will see the thermal stresses and strain concepts, and we will start with the definition. One of the definition that comes into the picture when you see the thermal strain and stress, that is natural deformation. Now, what is natural deformation? If prevented, the deformation due to the variation in the temperature is known as a natural expansion or natural contraction. As we all know that if you increase the temperature of any member, then it will try to expand a little bit more, and if you reduce the temperature of that particular body, it will reduce its dimension, and you can directly narrate that kind of a situation in this diagram. As you can see, the member is fixed on the one side and free on the other side. That is its initial position with the length of L. Now, if you increase the temperature of the body, you will see there is an increase in the length of the body by alpha T into L. How this comes, it will be explained in the next slide. But the body tend to expand freely, and due to the variation in the temperature, we have increased the temperature of the body, and that's why the length of the body is increased. So this type of expansion or contraction, both are known as a natural deformation. Natural deformation, free expansion, free contraction, both are the same terms. You will see this kind of a terms in the entire chapter. So we will see another definition, that is nothing but the thermal strain and stress. Now, what is thermal strain and stress? As we have seen in the previous definition, that if you are not preventing any deformation, then the body will increase its length or dimensions naturally and freely. And if the body is free to expand, then there will be no stress generated in the body, and that's why if you prevent the body, then body will resist that prevention, and due to the resistance, the body will suffer stresses, and or it will be subjected to different stresses. These stresses are known as a thermal stress. So the ratio of the prevented free expansion to the original length of the member is known as a thermal strain. This is the basic like the basic definition of the normal strain. Okay, this is due to the thermal variation, and that's why this is known as a thermal strain. Due to which the stresses are generated in the body. If you prevent the natural expansion, then the body will resist that kind of a prevention, and that's why the stresses will be generated, and those stresses are known as the thermal stress. Okay, so as we will take an example by this diagram, as you can see, the body would like to expand a little bit more if you increase the temperature of that particular member, and that is known as a free expansion, as we have seen in the previous definition. But what happens if you prevent the free expansion of that body, and now you increase the temperature of the body? As you can see in the second diagram, the body is prevented on the both side, and if you increase the temperature of that body, now the body tends to expand a little bit, but there is no gap or there is no area where the body is allowed to expand, and that's why the body resists that kind of a prevention, that kind of a both rigid supports, and that's why the body will resist it, and due to this resistance, the stress will be generated, and the main cause of this stress is nothing but the thermal stress, thermal variation, and that's why this type of a stress is known as a thermal stresses. So this was the basic two definitions, and now we will move on to the next topic, that is our formulas, which will be utilized for the examples. So the thermal stress and strain formula will be required to solve the examples. So first of all, consider the increment or a decrement in the length, which will be denoted by the delta L, and if the length is increasing or decreasing due to the change in the temperature, then that will be calculated using the equation, that is delta L equals to L into alpha into T. Now, what are these terms? So as you can see in this slide, that L is nothing but the original length of the body. What is T? T is the rise or a fall in the temperature. So we have not denoted it as a delta T. definitely it is a delta T or a change in a temperature. It is not an absolute temperature. We are taking the change in a temperature because change in temperature is the cause for this kind of a thermal stresses and strain, and that's why T is nothing but a change in a temperature. So that indicates the rise or any fall in the temperature from the present condition, okay, or the ambient condition. Next term is our alpha. What is alpha? Alpha is nothing but the coefficient of thermal expansion. Now this depends on the material of the member. There may be the different kind of a coefficient available for different material, and that will decide that how much expansion or the contraction will occur in that particular material. And that's why if the alpha is more, the material will tend to expand more, and if the alpha is less, the material will tend to expand a little less. Okay, this alpha is a constant and it is dependent on the material only. Okay, so alpha constant should be taken from the material properties. So now as you can see, we have found the value of the change in the length, whether it is an increase in a length or a decrease in a length. But if you want to find out this kind of a situation in the as an example, then you can see in this diagram that we have taken the same example of the previous slide, that we have considered a member which is fixed on the one end and which is free on the another end, and this member is subjected to a increase in the temperature. So the temperature variation is applied. Now that member will try to expand freely. Okay, so the free expansion should be calculated using the equation of the delta L, that is L alpha delta T or L alpha T. T is nothing but a delta T. Okay, so if you find out this free expansion, if you want to find out this free expansion, then you can calculate it as a L alpha delta T. Now, if you prevent this expansion, then the stress and strain comes into the picture. Now, if you prevent this expansion, then the body will resist this kind of a prevention, and due to this resistance, the stress will be generated, which we have already seen in the previous slide. So, first we will define the strain, and based on that strain, if the prevention is provided, we will calculate the stress. So, let's move on to the next step, that is, if the ends of the body are fixed to the rigid supports, so its expansion is prevented, the compressive strain induced in the body can be calculated as epsilon compressive is nothing but delta L upon L. So this is the very basic formula of the strain, where the formula is nothing but the change in length upon original length. Now delta L upon L can be simplified a little bit more, like if you put the value of the delta L, that is nothing but the L alpha delta T, and in the denominator there is only one factor, that is L. So as you can see, the L can be cancelled out from the numerator and the denominator, and our final simplified formula for the thermal strain could be written as epsilon C equals to alpha into T. Now in this case, we have prevented the expansion of the member, and we have applied the rise in the temperature. But what happens when you apply the fall in the temperature and still your member is fixed from both ends? Okay, so if you reduce the temperature of the member will try to contract itself. Okay, but you have fixed it, but you have prevented the motion of the free contraction of the member. Then the member will resist that kind of a prevention, and a tensile compression or a tensile strain will be generated into the member, and the nature will be different from the one that we have written over here. Okay. Now, if we want to find out the stress in this condition, so the stress is directly proportional to strain, and we can calculate the stress from the strain using the simple formula, and that formula is nothing but the thermal stress sigma Th is equals to epsilon into E. As you can see, E is the Young's modulus or a modulus of elasticity, then sigma Th is equals to alpha T into E. This is the very basic formula of the thermal stress and strain. Now we will see another one, if the supports are yielded. Now what is the meaning of yield? Yielding means they are subjected to a little bit of a relief. or you can say that there is a gap provided between the restrictions. Okay, if the rigid supports are placed with some gap, it can be seen from this diagram. There is a gap between the both rigid support and the end of the member. So what happens in this case, whenever you increase the temperature of that member, the member will try to expand itself. Okay, so it will expand, it will try to expand freely, but what happens, it can narrate the free deformation in the gap. Okay, the gap which is provided between the support and the end of the member. But what happened later on, whenever the gap is filled with the member body, then the support are fixed, and that due to this fixed support, the body cannot expand from that particular extreme limits, and that's why the body will face the resistance from that particular point. Initially, the body was free to expand to fill the gap, but later on, after the filling the gap, the body will face the resistance, and this resistance is the cause of the thermal stress. So the thermal stress will be generated after filling the gap. So during the gap filling, there is no stress generated in the body, and that's why we have to subtract the deformation during the gap, because the deformation during the gap is contributing the very less or the zero value in the thermal stress generation. Okay, and that's why what we will do, we will subtract the gap value from the deformation, and as you can see, the free expansion is prevented, which is prevented by the fixed support, which will be subtracted within the gap. As you can see, the thermal strain can also be represented by the E value instead of the epsilon. Both are the similar notation for the thermal strain, and E is equals to free expansions prevented minus gap divided by original length of the bar. So if you put each and every values of the this parameter, then you can see that the free expansion prevented can be written as alpha T into L. Now the gap which is provided will be given in your example already, so you will put that value in this equation, and divided by original length of the bar was the capital L. So if you put each and every values, then you will calculate the value of the actual thermal strain which is generated during the case where the body is subjected to where the supports are yielding. Okay, whenever the supports are yielding, you will have to subtract the gap from the free expansion. Clear? Now you can calculate the thermal stress value from this calculated thermal strain or actual strain in which you have considered the gap. Okay, so the thermal stress can be calculated using the basic formula of the thermal stress, that is nothing but the sigma Th is equals to alpha T into E. Okay, now we will move on to the next topic of this slide, that is example based on these concepts. Now we will see one of the example which has been asked in previous papers. That is a very basic example, but it will clear your basic ideas about the previous concepts of the thermal stress and strains. So as you can see, the data which is provided in the example is on the screen. A bar of a 3 meter long and 20 mm diameter. So the length of the bar is 3 meter. Capital L is provided as a 3 meter and the diameter is 20 mm. So the cross section of the bar is nothing but the circular. So we have a cylindrical bar. Okay, as you have to imagine that particular thing whenever you are reading the data is rigidly fixed in a 2 supports. So there are 2 supports and the ends of the bar are fixed within that support at a certain temperature. Let's say any temperature or a room temperature. Okay, if the temperature is raised by 60 degrees centigrade, now from that certain temperature you are increasing the temperature as a 60 degree, a little bit 60 degree more. Whatever the temperature of the room at that time, the bar was at 25 degrees centigrade, let's say for example. Okay, I am not saying that the 25 degrees centigrade is given in the data, but the thing is, if the room temperature is 25, then you are increasing the 60 degree more in that 25, then your final temperature would be 85 degrees centigrade. We don't know the current temperature and we don't require it, because we need only change in the temperature, and which is given as a 60 degree. 60 degrees centigrade is raised on that particular member. Okay, so 60 degrees centigrade is the change in the temperature which will increase the which will tend to expand the body, and due to that expansion is prevented, the body will face the stress in the material, and that stress is known as a thermal stress. Okay, so the question is that find the thermal stress. Okay, we need to find the thermal stress and strain of the bar. Also find the thermal stress and strain when the supports are yielded by 2 mm. Now yielding is nothing but providing the gap. Gap is provided of 2 mm. There is a gap of a 2 mm. Yield by 2 mm means there is a gap of a 2 mm. Take alpha equals to 12 into 10 raised to minus 6 per degree centigrade, and E is also given. Now what we will do? We will take a given data like this. Capital L is 3 meter. We will convert it into the mm, like a 3000 mm. Okay, alpha is nothing but 12 into 10 raised to minus 6 per degree Kelvin or a degree centigrade, both are the same, nothing difference. T is given as a 60 degree, E is also given. Now we will start our first step. In the first case, they have asked to find the thermal stress and strain where the both supports are fixed. There is no yielding, no gap is provided, both supports are fixed, and now you have to calculate the stress. In order to find out the stress, we have the basic formula of the stress. Which was the basic formula? Rewind the previous slide or rewind the video and see that particular formula of the basic stress, that is nothing but the alpha T into E. Now if you put each and every values, if you put the value of alpha, which is also given, T is also given, and E is also given, then you can direct simplify that values in the multiplication and get the answer of the thermal stress, that is nothing but the 144 Newton per mm square. Now if you want to find out the thermal strain, then the thermal strain and stress has a relation, and that relation is nothing but the sigma equals to E, that is thermal strain, small e, and into capital E, that is Young's modulus. The Young's modulus is also given, and you as you can see, there is only one unknown in this equation, that is E, that is small e, or a thermal strain, and that can also be written as a 7.2 into 10 raised to minus 4. Now as you can see, this value is having no units because the thermal strain is unitless quantity, and that's why you will have to understand that whenever you are writing the equation, whenever you are writing any answer, then those answers are unitless. Whenever you are writing the answer of the thermal strain, that answer is unitless. Okay, remember this thing when you are finding the answer of the thermal strain. Now we will move on to the second case. That was the case of when the supports were yielded by the 2 mm. So 2 mm gap is provided. As I said, whenever the gap is provided, you will have to subtract that gap from the free expansion. Then what is the free expansion? Free expansion can be calculated as alpha L into T. Alpha L into T, and if you subtract the gap from that particular free expansion, you will get the answer of the expansion prevented, that is delta L. So delta L is nothing but the alpha into T into L minus gap. Now if you put each and every values, to alpha value, T value and L value, and the gap is given as a 2 mm, as you can see this is the 2 mm, then you will find the final answer of the delta L as a 0.16 mm. Okay, now this was not asked in your example. They have asked about the thermal stress and strain, but you have found out the value of the delta L. Now you will have to calculate the value of the thermal strain. Now what is the value of the thermal strain? It is nothing but the delta L upon L. So if you put those two values from the above calculations, you will get the answer of the strain, which is also a unitless quantity. Okay, so make sure that you are not writing any vague unit like a meter or a mm. And now we will move on to the last thing which was asked in your example, that is thermal stress. And thermal stress can be calculated as a sigma equals to E into Young's modulus, and if you put those two values, you will get the answer as a 10.66 megapascal. So this was the end of our example, and now we conclude our lecture over here. In the next lecture, we will see a few more concepts of the elastic constant and continue our video lecture series. Thank you.